Study guide for the final exam. Problem 1. Find the greatest common divisor of these two numbers and the least common multiple of the same two numbers. First, we start with writing each of the numbers as a product of prime powers. If one of the numbers is not divisible by some prime, but the other one is divisible, we can write that the number that is not divisible by that prime is factored with that prime risen to power 0. This way, in both factorizations, we'll have the same prime and the same primes involved. Here we don't have a 0 exponent, but in some cases 0 exponent will be needed. Then we go over the prime powers to write the GCD. We pick the smallest of the two prime powers involved in both numbers. And for the LCM, we write the largest prime power involved in either of the numbers. Problem 2. Let D4 be the dihedral group, H be the reflection about the horizontal line through the center of the square, and R90 be the rotation about the center of the square on 90 degrees counterclockwise. Compute the product R90H and describe that symmetry. We label the vertices in counterclockwise direction, the vertices of the square, like this, and then R90H acts on 1, H acts first on 1, H is the horizontal line reflection, so 1 will go to 4. So H of 1 is 4, we can replace here H of 1 with 4. And then R90 acts on 4. R90 is counterclockwise rotation, so 4 goes to 1 on the R90. Similarly, we find R90 H of 2. First 2 goes to 3, and then 3 goes to 4. R90 H of 3, first 3 goes to 2 on the H, and then 2 goes to 3 on the R90. So as a result, this composition sends 3 to 3. And R90 H of 4 is first H acts on 4, it sends 4 to 1, and then R90 sends 1 to 2. What is this symmetry that sends 1 to 1, 3 to 3, and interchange 2 and 4? This is the symmetry about the second diagonal. It is denoted with D prime. So R90H is equal to D prime. Problem 3. List the cyclic subgroups of Z34. Z34 consists of the numbers from 0 to 33, and its operation is addition mod 34. We know that this group is cyclic, generated by 1, So the fundamental theorem for cyclic groups describes all subgroups. For every divisor M of 34, there is a unique subgroup of order M, and that subgroup is generated by the number 34 divided by M. And we have these divisors of 34, 34, 17, 2, and 1. And we get these subgroups. The subgroup generated by 1, the subgroup generated by 2, the subgroup generated by 17, and the subgroup generated by 0. By 0 here, because 34 mod 34 is 0. Problem 4. Let alpha be this transposition. It sends 1 to 2, 2 to 1, 3 to 5, and so on. Any number from the first row is sent to the number beneath it written in the second row. So alpha is a permutation from the symmetric group S8. To write alpha as a product of disjoint cycles, we open a cycle, write 1, and then after 1 write the image of 1, and the alpha it is 2, then the image of 2 and the alpha is 1, which means this cycle closes. We open a new cycle and write a number different from 1 and 2. The smallest such number is 3, so it is 3. Then 3 goes to 5, we write 5 after 3, 5 goes to 4, 4 after 5, and 4 goes to 3. So this cycle closes. We open a new cycle and write the smallest number not written yet. It is 6. Then after 6 we write 7. After 7 we write 8. After 8 we write 6. But 6 is already written, so we just close the cycle. So all the numbers from 1 to 8 are written now, and we stop. This is the decomposition of cycle of alpha as a product of disjoint cycles. B, write alpha as a product of transpositions. Any 3 cycle can be written as a product of transpositions. 2 transpositions. We write 3 first and then 4, 5. So we start from the end. 4, 5. 4 goes first, 5 next. And 6, 7, 8 similarly is a product of these two cycles. In each we write 6 and then 8, 7. One, 2 is already a 2 cycle, and we replace each of these 3 cycles with these products of 2 cycles, and we obtain alpha written as a product of 2 cycles. 2 cycles are called also transpositions. Problem 5. Determine whether or not U15 is isomorphic to U24. We know UN is the group of all numbers from 1 to n minus 1 that are relatively prime to n, and the operation of UN is multiplication mod n. Instead of computing orders and comparing them, orders of elements in each of these groups, we use a theorem that states that if n is factor as a product of two relatively prime numbers, then they say n is equal to n1 times n2, and n1 and n2 are relatively prime, then un is isomorphic to external direct product of un1 and un2. Because 15 can be factored this way, 3 times 5, and 3 and 5 are relatively prime, u15 is isomorphic to the external direct product of u3 and u5, and similarly we can factor 24 as 3 times 8, 3 and 8 are relatively prime, so u24 is isomorphic to u3 plus u8. And we need to compare u5 and u8. u5 is cyclic generated by 2, because 2 squared is 4, and 2 cubed is 8 mod 5, which is 3, and 2 to the 4 is 2 times 3, 6 mod 5, 1. So all powers of 2, this cyclic subgroup, is equal to the whole group. That's why u5 is cyclic, and 2 has order 4. Well, each element of u8 has also 4 numbers, because from 1 to 7 we have only 1, 3, and 5, 1, 3, 5, and 7 relatively prime to 8. And the order of each of these is 2, because 3 squared is 9, and 9 is 1 mod 8. So the order of 3 is 2. Similarly, 5 squared is 1 in this group, and 7 squared is 1. That is 3, 5, and 7, each of them has order 2. This shows that u8 is not cyclic. Well, u5 is cyclic, so u5 and u8 are not isomorphic, which makes u15 and u24 not isomorphic. Problem 6. Find the elements of order 2 in the external direct product of Z4 and Z6. Solution. The external direct product of these two groups consists of all pairs AB, such that A is in Z4 and B is in Z6. And we know that the order of a pair in external direct product is equal to the least common multiple of the order of the components. We want the least common multiple to be 2, and this is true if and only if these orders are 2, 2, 1, 2, or 2, 1. So we have to find all elements in the first group that have order 2 or 1, and all elements in the second group that have order 2 or 1. Since both groups are cyclic, they have unique subgroups of order 2. In Z4, this is the subgroup generated by 2. So 2 has order 2, because 2 times 2 is 0, and 0 has order 1 in the first group. In the second group, the unique subgroup of order 2 is generated by 6 divided by 2, which is 3. So 3 has order 2, and 0 has order 1. So the elements of order 2 in this external direct product are these pairs 2, 3, 0, 3, and 2, 0. 2, 3. In 2, 3, both elements have order 2 has order 2 and 3 has order 2. Here 0 has order 1, 3 has order 2 in the second group, in Z6. And for this pair, 2 has order 2 in Z4 and 0 has order 1 in Z6. Problem 7. Construct the Cayley table for the factor group U to any factor by the cyclic subgroup generated by 11. We know U to any consists of all numbers from 1 to 19 that are relatively prime to 20. So I write them down. And the operation in this group is multiplication mod 20. The subgroup generated by 11 consists of all powers of 11. Since 11 squared mod 20 is 1, we have only 2 different powers of 11 in this group U20. So the subgroup generated by 11 consists of these two numbers. The order of the factor group is equal to the order of the group divided by the order of the subgroup. The order of the subgroup is 2. It is just the number of elements in the subgroup. And the order of the group U20 is the number of elements. In U20 we have 8 numbers here, so it is 8. This means that the factor group will have 4 cosets. The first coset is just the subgroup. It is 1 bar. 3 bar is the subgroup the coset that contains 3. So 3 times the subgroup 11. Multiply each of the numbers in the subgroup by 3. You'll get 3 and 33. But 33 must be reduced mod 20. So it is 13. So in this coset we have 3 and 13. To get another coset, we pick a number from U20 that is not here and not in the second coset. The smallest such number is 7, so the next coset will be 7 times the subgroup 11. Again, multiply each of the numbers in the subgroup by 7. You have 7 and 77. Then reduce 77 mod 20. It is 17. So in the next coset we have 7 and 17. This way we have 3 different cosets. You see that they are disjoint. The last coset will contain a number that is not written yet in these 3 cosets. And the smallest such number is 9. 9 times the subgroup is the next coset. 9 and 99. Reduce 99 mod 20. You get 19. So we have the 4 cosets of the factor group. The Cayley table will be 4 by 4 table. The entries are the elements of the entries are the cosets. And multiplication is the way we do multiplication in factor group. We multiply the representatives, 7 and 9, 63. it must be taken mod 20 because in this group the multiplication is defined like that. And then we take the coset that contains that number. 63 mod 20 is 3, and 3 bar is the result. So 7 bar times 9 bar is 3 bar. And we fill out the table, continuing applying this for any two products. Problem 8. Suppose that phi is the map from Z30 to Z30, for which we know that it is a group homomorphism, and it's the kernel of the homomorphism consists of these three numbers. If it is given that phi of 23 is 9, determine all elements of Z30 that map to 9. Solution: we know that the cosets of Z30, the coset of Z30 that contains 23, the coset of the kernel that contains 23, consists of such numbers. Each of them maps to 9. So we have to find the coset of the kernel that contains 23. Because the operation in Z30 is addition, we have this coset 23 plus the kernel. So add 23 to each of these three numbers of the kernel. And addition must be taken mod 13 because the operation in the group is like that. So we end up with 33 mod 30, which is 3, 43 mod 30, which is 13, and 23. So each of these three numbers map to 9 on the phi, and only these three numbers do so. Problem 9. The set G, consisting of these numbers, is a group under multiplication mod 45. Express G as an external direct product of cyclic groups. Multiplication mod 45 is commutative, so G is a commutative group, and it has what order? We count the number of elements in G. So it is a group of order 12. The prime power of factorization of 12 is 2 squared times 3. And 2 squared, we write all possible representation of 2 as a sum of positive integers. We have only 2 such representations, 2 equals 2, and 2 equals 1 plus 1. So there are 2 abelian groups of order 4, Z4 and Z2 plus Z2, and there is only one abelian group of order 3. Then we combine each of these two possibilities with Z3, and we end up with 2 possible abelian groups of order 12, Z4 plus Z3, and Z2 plus Z2 plus Z3. So our group G is isomorphic to one of these two groups, and we determine which one by computing orders of elements. Z4 plus Z3 is isomorphic to Z12, the product of 4 and 3, because the GCD of 4 and 3 is 1. we know this theorem from the text. If the index is like here, 4 and 3 are relatively prime, then we have this isomorphism, and it is the only time that this isomorphism is true, when the index is relatively prime. So the first group, Z4 plus Z3, is cyclic, and it has a unique element of order 2. It is because Z12 is cyclic and has unique element of order 2, it is the number 6. For the subgroup, it is the pair 2, 0. For this group Z4 plus Z3, the unique element of order 2 is the pair 2, 0. We compute some orders of elements in G. 4 squared is 16, 4 cubed mod 45 is 19, 4 to the 4 is 31, 4 to the 5th is 34, and 4 to the 6 is 1. This shows that the order of 4 is 6 in this group, G. Hence, the order of 4 cubed will be 2, and 4 cubed is 19. So the order of 19 is 2, and you can see that directly from here. 19 square mod 45, compute that, you'll see it is 1. So 19 has order 2, and also 44 has order 2. So we have at least 2 elements of order 2 in G. This shows that G cannot be isomorphic to Z4 plus Z3, because in that group we have unique element of order 2. Therefore, G must be isomorphic to Z2 plus Z2 plus Z3. Proof or disprove that the set S, consisting of these real numbers a plus b root of 2, for such that a and b are integers, is a subring of the real number ring R. Solution: the subset S is not empty because any integer is in S. The subring test applies. First, we check that if we have two numbers from S, then their difference is also in S. And it is the case because A, B, C, D are integers, and therefore A minus C and B minus D are integers. That is, this is a number from S. And closure under multiplication is verified easily too. The product of these two numbers, use the distributive law, and then collect like terms, you end up with this. Again, since A, B, C, D are integers, the number in this parenthesis is an integer, and this number here in the second parenthesis is an integer, which means that this sum belongs to S. So S meets the requirements of the subring test, and For that reason, S is a subring of the real number ring. Problem 11. Find all zero divisors and all units in the ring Z9. The elements of Z9 are the numbers from 1 to 8, and the operations are addition and multiplication mod 9. Since 9 is 3 squared, the zero divisors are the non-zero multiples of 3, and these are 3 and 6. And we see 3 and 6 are non-zeros, but 3 times 6 is 0 mod 9. So 3 and 6 are zero divisors, and there is no other zero divisor in Z9. And the units are all other non-zero numbers in Z9. 2 times 5 is 1 in this ring, 4 times 7 is 1 in this ring, and 8 squared is 1 in this ring, which means that the multiplicative inverse of 2 is 5, the multiplicative inverse of 5 is 2, similarly 7 and 4 are multiplicative inverses of each other, and the multiplicative inverse of 8 is 8. So the units are these numbers. 1, 2, 4, 5, 7, 8. Problem 12. Since 19 is a prime number, the ring Z19 is a field. Find the multiplicative inverse of 16 in this field. Solution. Since the greatest common divisor of 19 and 16 is 1, there are integers s and t such that 19s plus 16t is equal to 1. We find s and t using the Euclidean algorithm. Start dividing divide first 19 by 16, you get remainder 1, quotient 1 and remainder 3. Then shift 16 here, shift 3 here, divide 16 by 3, you get quotient 5 and the remainder 1. And this means that 1 is the GCD, the next shift will produce a remainder of 0. So 1 is the last non-zero remainder. And we work backward to find s and t. From the last equality, we write 1 as 16 minus 3 times 5. And then from the first equality, we express 3 as 19 minus 3. And we replace this 3 over here with 19 minus 16. Then 16 and 19 must be kept as factors. We distribute 5 here, and the negative sign. So we have 16 minus 19 times 5 plus 16 times 5. We keep 16 and 19 as factors. Then collect how many 16s we have. We can write 1 this way from here. Then factor out 16. So we have 16 times 6 plus 19 times negative 5. So So this S is -5 and T is 6. We found S and T. From this, we can take congruence mod 19, because we are in Z19. 19 is 0. It disappears here. This shows that in this field, 16 times 6 is equal to 1, and thus the multiplicative inverse of 16 is 6. With this we have this equality.